Okay, because the region of integration for a double integral is in the xy plane, we can take the region to be more general than just a rectangle. So in this diagram here, we have a region where the top and bottom boundary of the region is now curved. So basically, the setup for a type 1 region is where the boundary on the left and on the right for x is given by a and b, and they're just vertical lines like this. But again, y is allowed to vary between these two curves. The bottom curve is represented by the function g1 of x, and the top curve is represented by the function g2 of x. So written out, we would describe the region like this, where x varies between the two numbers a and b, and y varies between the two functions g1 of x and g2 of x. So when we go to set up the double integral, because the outer integral has to be an ordinary integral, and x is the only variable that varies between two numbers, the outer integral has to be with respect to the variable x, and the variable y, which varies between two functions of x, is set up as the inner integral, right? So the inner integral is a partial integral, and if you remember back in the first page, a partial integral is allowed to have a variable in the limits of integration as long as that variable is different from the variable of integration. Right, so you see here in the inner integral, x is being thought of as a constant, so the two functions g1 of x and g2 of x are allowed to be the limits of integration for the variable for the variable y. And just as before, if f is a positive function, you can think of this double integral as representing some kind of volume between the surface of the graph and the region and the region R. Okay, so now with this setup for a type 1 region, let's take a look at an example. So in example 4, we're given that the region R is bounded by the graphs y equals x, y equals 0, and x equals 4. So first, let's try to visualize this region. Right, so the line y equals 0 is just a horizontal line that's right on top of the x-axis. So that's the line y equals 0. The line x equals 4. So say x equals 4 is somewhere here. So that would just be a vertical line like this. And then the line y equals x is just the slanted line like this with slope 1. So y equals x. And so the three curves bound this region in the middle here. So this is my region R. Okay, so here, if we want to write a description for this region, right? So you see the left end of the region stops here, and then the right end of the region stops here. So x varies between 0 and 4, and y, so the bottom boundary is just given by this horizontal line, which is at y equals 0, and the top boundary of the region is the line y equals x, right? So here the top boundary is x. Right, so we see this is the setup for a type 1 region where x varies between two numbers, and then even though the bottom boundary for y is a number, the top boundary contains the variable x. Okay, so so this is the description of the region, and so now we can set up our double integral. So the outer integral has to be with respect to x, right? So that goes between 0 and 4, and the inner integral is with respect to y. Y goes between 0 and x. My function is just 4e to the x squared minus 5 sine of y. Again, the inner variable was y, and then the outer was x. Okay, so so that's the double integral, right? So just as before, we calculate inside out. So this inner integral needs to be calculated first. So the outer integral stays the same. Okay, so we're integrating with respect to y, right? So here we're thinking of x as a constant, so this whole term is just a constant, and the antiderivative of a constant is a constant times y. So this would be 4e to the x squared times y, and then here again y is the variable, so the antiderivative of sine is minus cosine, but because of this minus sign, minus minus becomes a plus, so this is plus 5 cosine of y. And this needs to be evaluated between 0 and x. Okay, so again, the variable is y here, so I plug this in for y. So the outer integral is still there. We haven't done anything with that yet. So again, this goes in for y. So let's move the y over here. So it becomes 4x e to the x squared. And then we plug x in for y here, so you get plus 5 cosine of x. Okay, so that's plugging x in. Now we plug in 0. Again, still plugging in for y. So you get 4e to the x squared times 0 plus 5 cosine of 0. Okay, so this term here is multiplying by 0, so that goes to 0. However, we have to be careful here. Cosine of 0 is 1, and so 1 times 5 is 5. Okay, so this term here is 5, right? So so let's clean this up a little bit. So we still have the integral from 0 to 4, 4x e to the x squared. So what I'm going to do is I'm going to separate these integrals, right? Because if you have a sum of things, you're allowed to separate the integral. This integral is going to eventually need u substitution. So let's separate that out, and then the rest of the integral we calculate separately. So 5 cosine of x, and then this was minus 5, right? Because cosine of 0 is 1. Okay, so let's calculate this integral first, because this is fairly straightforward. This is just an ordinary integral, right? So antiderivative of cosine is sine, and then the antiderivative of a constant is constant times the variable, which in this case now is x, and I need to evaluate at the endpoints. So plugging in for x, you get 5 sine of 4 minus 5 times 4 is 20, and then minus 5 sine of 0 minus 5 times 0. Again, sine of 0 is 0, and then 5 times 0 is 0. So this whole term is 0. Okay, so this is the calculation for this part. Now let's go back to this thing. So as I said, this requires a u substitution because the derivative of x squared gives me 2x, and then I can cancel out this x here, right? So we take u to be x squared. Du, derivative of this is 2x times dx. So I can move the 2 to the right hand side by dividing, so you get 1/2 du is equal to x times dx. Okay, so what do I get here? Right, so the x times dx, so this x and the dx becomes 1/2 du. So I have to be careful, right? Because I've changed the variable, but this limit of integration was with respect to x. So let me make a note of that. So the 4 is still there, right? So again, x times dx becomes 1/2 du. So times 1/2 e, and then the x squared becomes u. Okay, so that's this integral here, and then now we take the antiderivative, right? So 4 times 1/2 is 2, and the antiderivative of the exponential function is just the exponential function, and then now I can plug the u back in, so this is x squared, and so now I've gone back to the variable x, so now I can just write 0 and 4. Okay, so so what do I get? Equals, so plugging in 4, so 4 squared is 16, so you get 2e to the 16, and then plugging in 0, e to the 0 is 1, so 1 times 2 is 2, so I get 2e to the 16 minus 2, but that's not everything, right? Because I don't want to forget this part here still needs to be calculated. Okay, so I still have plus 5 sine of 4 minus 20. Okay, so that's the whole calculation, and to save time, I've already calculated this previously, and this should come out to be approximately. It's a very large number because of this e to the 16th power. So it comes out to be 1772195.26. Okay, so this is how we calculate a double integral over a type 1 region. Right, so again, in the type 1 region, x varies between two numbers, and then y could vary between something that contains the variable x. And so when you set up the integral, the inner integral has to be with respect to y. And then you just proceed. The procedure of calculating the double integral is similar to before, right? So you just have this extra x here floating around.